Hi everyone! This is the last lesson. Congratulations. And it should be a really, really short one. So, what I'm going to be talking about today is Euler's method. And Euler's method, Euler was a really smart mathematician. You might have heard of him. He may have come up with the number E, or at least expressed it in algebraic terms. But Euler was like, I have this differential equation. Say I'm looking at dy dx equals x plus y. And I want to find the solutions to it, right? So to find my particular solution, I'd have to do separation of variables, and then I'd have to do the integration and the antiderivative, essentially, right? And then find the value of c if I want to find the particular solution. If you don't remember, right, if I have dy dx equals x, then I can say that y equals x squared over 2 plus c, some function like that. This is easy to solve that differential equation. But this differential is a little bit harder because the separation of variables is tricky when I have that x plus y. So up to this point in calculus, we don't know how to solve these quite yet. So Euler was like, well, I really want to be able to estimate what this value is over here, and I only know this value back there. So if I only know this value back here, well, I know before we've talked about tangent line approximations, but if I'm trying to find a value way over here, that's really not a good approximation for what that curve is. So what Euler did is he said, well, since I know tangent line approximations, what if I did a tiny tangent line from my point using the slope for a little bit to another point, maybe like half an x value away or something like that. And then I go from this point, I find the slope of my curve, which is the dy dx, and I take that slope and I go another set distance away using a tangent line. And then now from here, I'm going to use this positive slope now from this point that I found to do another tangent line. Right, so on and so forth. Oh man, until I can get to an approximation for my curve. It's still not going to be perfect, but it is a lot better of a representation of what the slope actually is, or what the point actually is, what the solution would be way out here. Way better than just using a tangent line approximation. This is the number of steps. So I have 1, 2, 3, 4, 5 steps on this one that I drew. The more steps that we use, or the smaller our tangent lines, the smaller our change in x, the more accurate we will be. But this is Euler's method in a nutshell. So still, I'm going to be using my tangent line approximation, so y equals y1 plus m x minus x1. The y1 and the x1 are your previous point. So that will change. So from my first tangent line, I used this back point. And then once I got to this point, I used this point to find the next one. And then I used this point to find the next. And then this point to find the next, and so on and so forth. So looking at our equation, right, y1, and I just have delta x, we'll see why in a second. And my slope is going to be based on the slope of my point that I'm coming from. This is Euler's method. Again, like I said, really all you need is the y1 plus m times x minus x1, right? And then using that, we can come up with our solutions. So given the differential equation, the x plus y, I can't really find a particular solution or a general solution in this case. But I'm going to say that y is the particular solution, y equals f of x, with the initial condition that f of 4 equals negative 1. Using Euler's method, they're always going to specify whether they want like a tangent line or Euler's method or whatever. Starting out from 4, from what I know, with 2 steps of equal size, approximate f of 4.2. Well, if I'm going from 4 to 4.2, each step size that I will want, or my change in x, will need to be 0.1, such that the first value that I can approximate is f of 4.1. And that is about, right, my y1, my previous point, so negative 1, plus my slope. My slope is going to be my differential at my previous point, so let me write that out. This is probably where you're going to mess up if you mess up. 4 negative 1, and then I can throw it into my equation, 4 minus 1, which is 3. So my slope will be 3 times x minus x1, so 4.1, which is what I'm trying to estimate, minus my x1, which would be 4. Notice this 4.1 minus 4 will be the same as your change in x, which is why in Euler's method we can just say it is delta x there. Okay, but then I can do that math. This is negative 1 plus 3 times 0.1, which is negative 0.7. All right, there's my first one. So the next one, I am going to have to go from my point at 4.1, negative 0.7. So to estimate f of 4.2, what I'm really trying to estimate, it is the y value of my previous point, so negative 0.7, plus my slope, so dy dx, at 4.1, negative 0.7, equals 4.1 plus negative 0.7, which is 3.4. So 3.4 x minus x1. You could do 4.2 minus 4.1, but again, that will just come out the change in x, which is 0.1. So this will be negative 0.7 plus 0.34, which will come out to negative 0.36. That is my estimation using 2 steps with Euler's method. And one thing they could ask you is, how could I make this a more accurate representation or a more accurate estimation? And the answer to that, like we were talking about before with our graph, right? The smaller that I make my what we call step size, the more accurate that I will be able to get an estimation of what that actually would be. So that's the whole deal. It's either like smaller step size or using more steps is the same sort of deal. And that will give us a more accurate representation of our approximation. Okay, so moving on. This chord does not like me. So let y be the solution to the differential equation, 1 plus 2x minus y. Again, this is something that I'm not really going to be able to work through finding a particular solution or even finding a general solution. Sorry, my cord is bugging on me. My AirPlay is not wanting to work, as you see. All right. Okay, let's try this again. So y of x is the solution to the differential equation of this. Again, that is something that I'm not really going to be able to find a particular solution because it would require a separation of variables. And I can get the y to the other side by adding a y over there, but when I multiply by dx, it's not really going to work out. So with the initial condition that f of 1 is 2, what is the approximation of f of 2? Starting at 1 using a step size of 1/2. So they're not telling me how many steps here, but they're actually giving me the step size. So all that means is that my delta x is 1/2 or 0.5, whatever you want to see that as. So the first approximation that I would do would be f of 1.5, and that is approximately from my previous y value, which is 2, I'm going to go the slope, right? So dy dx at the point 1, 2, and I'm going to plug that into 1 plus 2 times 1 minus y, which is 2. So that will be 1. So my slope here is 1, and then times x, which my x value now is 1.5, minus my previous x, which is 1, so that is just the step size. So this becomes 2 plus 1.5. Oh, no. 2 plus 0.5, right? Which is 2.5. And then I can use that point, 1.5 comma 2.5, right? That gives me the estimation, 1.5, 2.5. So then from this point, I'm going to do another tangent line approximation to find my approximation for 2, which is about 2.5, my previous y value, plus, again, this will be dy dx from my previous point, which is 1.5, 2.5, which will be 1 plus 2 times 1.5 minus y, which is 2.5, and that is equal to 1 plus 3 is 4, minus 2.5 is 1.5, so 1.5 times delta x, which is 1/2. Half of $1.50 is 75 cents, plus $2.50 is $3.25 holla. And that would be my estimation. So f of 2 is approximately 3.25 using those two steps. And that's really it. That's all we're really going to do with Euler's method. Sometimes we can go backwards with this stuff, but as you work through the worksheet, you will kind of see those things pop up as well. But as always, let me know what questions you have, and after this, we're just going to practice and get ready for our AP test. But congratulations, you did it. You have made it through BC. Now it's just time to take a bunch of tests. Aren't you so excited? Oh yeah.